Okay, yeah, it started. So you can see my screen, right?
Yep.
Okay, great. So I think Arshit went through the whole basics about gates and the different kinds of gates. But this time, I'll be covering more about the math behind what the gates are, and also we'll be looking at the visualization of like how quantum gates can be visualized. So before we do quantum gates, there are two things we need to recap. One is a Dirac notation and one is block sphere. Direct notation because we need like to kind of write in a easier form. You can't use a matrix form every single time. And we use a block sphere because when it comes to different phases, um, or especially when you're using the complex number form for representing a qubit, we need the block sphere to visualize better. So about direct notation, we this was made because once your qubits increased, the matrices became bigger, and it was difficult to handle such big matrices. Hence, the direct notation was made. So writing this qubit form into the direct notation. So like the concept behind it, let a qubit be like alpha and beta, like two random coefficients. So you factorize them, and then you're left with like a column matrix of 1, 0, and 0, 1. So as Arshit had explained previously, these are nothing but your ket vectors. So once you get the factorized form out, you can write any matrix or any qubit in the form of the coefficient and the ket vectors. So this is more or less about the direct notation. So hence the previous question can be written in this form, wherein the first part of the column matrix will always have the ket vector 0, and the second one will have the ket vector of 1. So this is the basic crux of the direct notation. So a couple of questions which I've kept in the thing to understand it better. But let's just skip to like the block sphere. So a block sphere is basically a sphere wherein a point on it can be a qubit. So imagine like in complex numbers, you had like a 2D plane. So one was your real axis and one was your imaginary axis. But here you have like three kind of like axes. Hence, you have a sphere. So you have like a positive axis, you have a complex axis, and you have an axis to represent your I mean your superposition of 0 or superposition of 1. So that's your block sphere. So if we have like a point which is like higher on the z-axis, where the z-axis north is your ket vector 0. So the more north you go, it means that there's a higher probability of measuring that qubit as a ket vector 0. But if we are like at the tip of it, that means your probability that the ket vector is like 0 is like, like high. So that's like 1. So that qubit is basically the ket vector 0. So if you're on the tip of sphere, that's the North Pole, it's 0. So similarly, if you're on the tip of this, you're at the South Pole of the sphere, that means your ket vector is 1. So that means the qubit, which is like 1. So that's it. So how can we okay, yeah, so your let's just like consider a qubit, which is 1 over root 2, both the values for a column matrix. So this can be like represented as like a straight line, okay, and it has an even chance of being measured as either 0 or an even chance of being measured 1. Because if here your alpha and beta values are 1 over root 2, so once you square it, you get one half. So the probabilities are the same. So you can represent it anywhere on in this case, the XY plane. So it can like kind of like be here as well. It can be in the center here, like in the middle, but anywhere on the XZ plane because you have the equal probability of measuring here. So now, why do we need like these phases here, which is your y-axis and your x-axis? That I'll come to like later, but for now, like this is just the basic representation. Again, like this state, where will this state be? Where you have half and root 3 over 2. So again, if you square it, it's like 1/4 and you have 3/4. So it will be more over the south side because there's a higher chance it's being measured as 1. And it'll be less towards the north side because there's a lower chance of being measured as 0. So it lies somewhere in this kind of plane. So it can either be here or it can be even on this side. I hope you can see my mouse pointer. So this is the whole concept about the block sphere. Now, coming to your three main basic single qubit gates, which is X, Y, and Z. Okay, so Um, okay, so let's just consider like a vector, which is as shown here. So it's like at the tip of the sphere on north, and it's 0. So if you apply the X gate to it, which is the X gate is also called the NOT operator. So typical sense, it'll just flip. So the X gate basically just flips a vector as shown here. So if this was the original one, this is the flipped one. So this is the purpose of the X gate. It just flips. And here your XY plane is your mirror. So it becomes easier to imagine if this is your mirror plane, it just flips over it. So that's the whole concept about an X gate. It is very simple. Again, if we have something here, okay, here your plane, okay, here your Z axis will be like the line, okay, when it flips over. So if this is your case here, it's gonna flip and come on the other side. So it's just a NOT gate. That's your X1. So the whole X gate flips a qubit pi radians around the X axis on the block sphere. So that's why the X gate, because it flips over the X axis. Coming back to the Y gate, as you might have guessed, it just flips it over the Y axis. So again, here in this case, your ZY plane becomes the mirror and the Y, what do you call it? The Y axis becomes the mirror line. So if you have a vector like this and you apply the Y gate operation over it, it just flips on the other side. So it flips again pi radians on the Y axis. So that's your basic concept about a Y gate. Z gate, again, it just flips over the Z axis. So that's all the three, okay, basic gates together. The X gate is called the NOT gate because it primarily works on the axis wherein you have the superimposition of 0 and 1. So yeah. And the XYZ gates are also their own inverses. So if you have like one qubit and you do like one X gate operation on it, and again you do like the same operation on it, it's just gonna rotate 360 degrees. So it'll just like land up in in its original state. Hence, it's like their own inverse. So not all gates are their own inverses, but this one particularly is. Okay, coming to the matrix representation. So this is where the math lies, okay, of the gates. So each of these gates are represented by like a matrix. So how you have the identity matrix, similarly, a gate, okay, is represented by a matrix. This is very not typical about Boolean algebra because in Boolean algebra, I do not have like a mathematical representation, but you just have symbols. But when it comes to quantum computing, you're dealing with like linear algebra, and that's why hence most of the operations are linear algebraic operations, and you have like matrices for the same. So the X, Y, and Z gates are represented as like matrices here. So if you have like a qubit, let's say like a qubit, which is column matrix alpha and beta. So if you apply the X gate towards it, it just flips. So that's how it is. So that's how the whole concept about an X gate is. You just do basic matrix multiplication here, and that's how you land up with the answer, beta and alpha. So, okay, so applying an X gate on get vector 0 gives you like 1. That's because if we like visualize here, like the very first visualization which you have done, wherein you have a ket vector 0, which is the tip, and if you apply the X gate, So you get 1 here. So the same concept here is shown in like mathematical form, wherein if you apply the x gate, which is the matrix form on the ket vector 0, you get the inverse, which is 1. So that's the whole concept. And here you can clearly make out it's a NOT gate using mathematics. So it's pretty similar, like using a block sphere and like doing the mathematical form, you get the same answer. So another property about this is like if you have any random gate, like a gate is basically a matrix operation um, in like quantum computing. So if you have a gate which is like given by like A, B, C, D, you can split it. So basically you can take one row, okay, and you can write it in the direct notation. So here, essentially what you're doing is you're taking the row matrix, sub matrix of this, and you're writing it in this form. Okay, so you can kind of write it in like this manner. It's a very important property when you're dealing with like higher gates. But for basic ones, you don't necessarily have to split it because you can easily multiply. So another very important property about quantum gates is if you're having a gate which is operating on like a qubit, so you can kind of distribute this gate over both the parts of it. So that's one more thing to keep in mind. It works this way. So this is the linear property of quantum gates. Now applying the Y gate to this. So again, like here you have complex numbers. We'll come to why this gate has like quantum, I mean, not quantum, but complex numbers here. So once you apply this, this is your answer. So let's just say you have a gate which is root 3 by 2, ket vector 0 plus half into ket vector 1. So if you apply the Y gate, you get this answer. Yeah. This is more on the whole how you get it. And you can get the complex number out, okay? And you can leave the inside the matrix to convert it into the direct form. You can just leave a 0 and 1 or a 1, 0 inside. So if once we had like this, so you can kind of check here that, like the phase also changes. You're not just inverting it because here there's even a complex number which gets added. This is unlike the X gate wherein it was just inverting, but the Y gate is not like that. It changes phase as well. So coming to the Z gate again is the same thing, yeah, wherein um, you get a change of sign. That means the magnitude remains the same, but there's a change in the phase. So the Y and the Z gates not necessarily just flip the thing. Okay, I mean they also change phases. So coming to the two different kinds of phases which is there, I think Arshid had covered this in the last lecture. So phase, it might not look that useful for now because at the end the magnitude remains the same. So if you're either measure, it's like let's just say like this plane, when the XY plane here, you take a vector anywhere in this plane, its magnitude is gonna be the same, no matter how you represent it. But only the thing is gonna change is the phase. So again, it looks kind of useless in the start, but soon, like I mean, it is like one of the most important like parts, like of quantum computing. It makes it like so powerful only because you're dealing with phases here. So consider like this qubit. Again, like this basic one, which is like 1 over root 2. So if you kind of apply the Z gate here, the magnitude remains the same here. Okay. Just repeating what the magnitude here will be, it's going to be the square of alpha and beta. In this case, alpha is 1 over root 2, and here beta is negative 1 over root 2. So if you square them, you get the same value. Okay. Here, before applying the Z gate and after applying the Z gate. So again, here it's just rotated. Okay. It's not like changing the magnitude. And in quantum computing, you can represent all the complex numbers in the form of e raised to I pi. So this is the exponential or the Euler's form of representation of a complex number. So usually you prefer this form okay, over the traditional Cartesian format, because we deal with like block spheres and we deal with like majorly rotation. So for such things, your exponential form plays a vital role because the phi value here, so leave alone the e raised to I, but this phi which is there tells you how much the whole rotation is. So if you have a vector and if you're performing any operation either via gates or a normal tensor multiplication, um, it's the phi value which will tell you like how much the qubit value has changed, like not just in the magnitude here, but in the case of like direction or like phase. So that's the whole reason why we use an exponential form instead of using the normal Cartesian coordinates or Cartesian form when you deal with like qubits and complex numbers as usual. So okay, in this case here, so you have the same vector again. So you can just, if you're like rotating it here, so if it's like here, okay, like it's on the x-axis, so on the positive x-axis, and you're making a rotation of like 90 degrees here, which is pi by 2. So it's gonna go on this axis, which is the I-axis. So there'll be a phase change of I. So here, when you're writing this thing here, you can write I as e raised to power I times pi by 2. So again, the phi value here, okay, the phi value here will tell how much the phase is changed of the original vector. So that's the whole concept about how you deal with the exponential form of qubits. I mean, when it comes to like the direct notation and why this is more preferred. This is only because to show the rotation. So, yeah, I think this is self-explanatory. By multiplying the ket vector 1 by e raised to power I phi, sorry, we rotate around the z-axis on the block sphere by phi radians. So this is the whole concept here. So, a basic question, if we have the qubit in superposition and as a relative phase of e raised to power phi pi I by 4. So on the block sphere, and how many radians has the qubit spun? So again, the answer here is phi pi by 4 radians because again, you can see like the phi value here is essentially phi pi by 4. So basic question um, on the whole concept about block spheres and rotation and phases. So now we are mostly dealing with like phases. So if you check all the previous examples here, we do not operate the phase on the uh, zero ket vector, but essentially we are doing it only on the one. So again, like every case here, which you see, we are dealing it only with the one ket vector, not on the zero one. So this phase, this type of like representation is like called a relative phase. But there is also another form called as the global phase representation. So the thing is, this is physically irrelevant because if you multiply the entire qubit with an exponential or with a complex number here, you can just factor it out. So essentially, the whole qubit is on the same like what do you call it? On the same axis or on the same, it's on the same vector, but just you're adding a different magnitude in front of it. So that's why you basically discard the global phase and you don't like consider it when it comes to like of as a phase change. But instead of the relative one, you can clearly see that there is an actual phase change which is happening, unlike the global phase. So that's the whole reason why you kind of dismiss the global phase and you only stick to the relative phase. Another example of it, if you have the same, again, the same qubit value, you're multiplying it with another thing, essentially it remains the same once you factor out the whole thing. So the direct representation remains the same, it's unchanged. That's why we do not consider the global phase. Another thing here, so if you do have like a relative phase which is changing, the magnitude remains the same here because um, your alpha, which is here, okay, that remains unchanged. But once you take like the beta form of it, okay, here your the complex number will come into the picture. But the complex number's coefficient, okay, is one here. Like the form, the Euler's form, which is there, is basically R in times e raised to power I phi. So this whole form, okay, where the real part is the r. Okay, these are like polar coordinates. And here in this case, the r value is 1. So even if you have a kind of like a complex number which is coming as a phase change, you do not necessarily change the magnitude of the qubit. So that's why like the magnitude remains unchanged, but you're just changing the phase. So this is like one mathematical proof of the same. Why does relative phase matter? Uh, so the answer for this is the Hadamard gate. What is the Hadamard gate? I'm coming to it. So again, like if you have like seen the block sphere here, on your z-axis you have the ket vector 0 and the ket vector 1. But the other two axes which are there, one of them is the negative one and the positive one. Another one is the complex one, where you have positive I and you have negative I. So these axes can be written, okay, as like this format. So if you consider the positive one, which is this one, the positive x one, it can be written as 1 over root 2 times the ket vector 0, because it's equally aligned to it. So there's equal probability. So that's why you use this whole representation of these axes. They're like equations of the line, you could say. And your ket vectors play the role of x and y. It's as simple as that. So these can be written as this format. Okay. So what the Hadamard gate does, okay, so this is the Hadamard gate, first of all. It's again a matrix with like a coefficient. So what it does is, if you have the 0 ket vector, so once you apply it on 0, it converts this whole thing to positive. So again, so if let's just consider 0, okay, here, okay, and once you apply the Hadamard gate on it, it just shifts like 90 degrees without any change of magnitude. It shifts from the z-axis all the way to the x-axis. So that's what the whole Hadamard gate is. Okay, it's not changing the magnitude at all. Okay, nor like it's like, I mean, altering the whole qubit as a whole. But what it does is it just changes the phase. And the Hadamard gate again is its own inverse. Because if you apply the Hadamard gate on the positive, on the plus axis, you get 0 back again. So similarly for 1, if you apply, you get negative. And if you apply for negative, you get 1 back. So again, the Hadamard gate is its own inverse. So this is the whole mathematical representation of it. So if you're applying the Hadamard gate, okay, on this qubit, so again, using linear properties, you distribute the Hadamard gate and then you kind of change it. So Hadamard on 0 gives positive, Hadamard on 1 gives negative. So again, the positive one, the positive axis, if you refer back to this table, is written as 1 over root 2 times the ket vector 0 plus 1 over root 2 times the ket vector 1. So you expand this as this, okay? Then again, you take alpha inside and you simplify and write it in this form. So here what you're doing, if you can see like the initial one and the like later one, this is the operation of the Hadamard gate. So yeah, I think that's it for now. So okay, this is like about Hadamard gate. There are more complex illustrations on the same, but we'll like stop it here because once you go too much deep into it, it's like never ending on the Hadamard gate. There are more powerful visualizations available in the Hadamard gate, which you need to check out. Okay, now coming to the whole why this whole Hadamard gate thing is like very important, because once you like apply this here, okay, you get like you're basically just changing your phase here. So if you're positive, it becomes like 0, and if you're like negative, it becomes 1. So that is the whole operation of Hadamard gate and why phase in general is very powerful when it comes to quantum computing. Now the next two gates are your S and T gates. So these are like your S and the T gates. So what they do is basically they like increase like they they change your phase by like pi by 2. So it adds a relative phase of like pi by 2. So if you have like a qubit here, so once you apply the S gate on it, you get like e raised to like you're rotating it pi by 2. But when it comes to T gate, you're applying by 45 degrees. So like you're changing the relative phase by 45 degrees. So that's the whole concept of like an S and your T gate. Now, if your S dagger, so okay, so now coming back to S dagger, so your S dagger is basically your so if you have like S dagger here, it's of this format. The matrix is of this format. So it's like a negative pi by 2 rotation, which is negative 90 degrees. So it's gonna go the other way. So this is your representation. And S times the S, what do you call it? The S dagger gives you the original vector. So again, in the like how I had mentioned previously, not all gates are the inverse of each other. So in S and T gates, it's the dagger form which is the inverse. So this is the whole proof about how you want to get back the original one. You have to apply S dagger on it. So if you're applying the S gate, you apply S dagger back on it again, and you get the original format. So S into S dagger gives the original qubit. But if you go to compare the X, Y, and the Z gates, X, Y, Z and the H gates, they are the inverse of each other. So if you apply the gates twice on the same vector, it gives you the same vector back again. But if you apply the S vector once and you apply it the second time, it doesn't give you back the original vector. So that's one point to note where S and S dagger are the inverse of each other. Okay, so another part is like, so till now we were dealing with like one qubit. So what if like you get like two qubits, like in the form? So here something called the tensor product comes to the picture. So if you have like the zero ket vector and you're taking a tensor product of it, it's written in this format. So sorry. Okay, so if you have like two vectors here, and one is having coefficients alpha, beta, and one's having gamma and delta. So once you multiply them, you get all the different kind of like combinations possible. So you get like a 0, 0 with the coefficients of 0 here. You get 0 and 1 with the coefficients of 0, 1. And you get 1 and 0 with the coefficients of like 1 and 0. And then finally you get like 1, 1. So it's very simple tensor product. So we need to like kind of like understand this for like dealing with like multiple qubits at once. So that time you can use tensor product. That's the rule of multiplication. Now, again, once you take the tensor product, the probability which is there, it's the same thing. So you take the magnitude of the coefficient of the ket vector. So if you have the ket vector 0, 0, you take the coefficient of it, you get, and then you square it. So that's your whole magnitude. And we know that the magnitude of the ket vector gives you the probability of measuring it. So it remains unchanged here, even if you take a tensor product. So taking a more numerical example here, if you have this vector and if you're multiplying it with this vector again, and you're taking the tensor product of it, so this is your answer. This is how you solve it. It's very simple, just multiplication. But you need to make sure that you're considering every case of it, like here 0, 1, and if you're like multiple, so like 3 will come. So that's how you like kind of multiply. There's even a shorthand notation for it. So if you have multiple zeros, like let's just say like you have n number of qubits which are multiplying together and taking a tensor product of it. So you write it as this format. So this is how you write it. You write the 0, and then on top of it, you take like a tensor across and you write n. So it represents that there are n number of zeros in this. So again, when you deal with like a large amount of like matrices or like vectors, this is how you write like the shorthand notation. Now, coming to the last and the actual application of the gates, I would say that comes under quantum circuits. So this is essentially a quantum circuit. Um, what happens in a Boolean circuit is that if once you can take like measurements everywhere. So you remember like we used to have these complex circuits in like digital designing. So in that, what we used to do is at every part, like after every gate like operation, we used to write what do we get. So like let's just say there was like an X and a Y here, and let's just say this was like an OR gate. So after the OR gate, we used to write like X plus Y, because after each gate operation, you could observe the product, observe the result which you get after that gate operation. But the thing when you deal with quantum circuits is as soon as you take a measurement, okay, there is no longer a superposition and the whole superposition collapses. So that's why you have these special boxes and these represent your measurements. Okay, I hope you can see my pointer here. So the three boxes at the very end are is when you take the measurement of the same. Here the here are your basically like your qubits or like your superpositions, your get vectors, and the down like down where you have phi 0, phi 1, phi 2, phi 3, phi 4. These are all positions at which you kind of observe these quantum circuits. I mean quantum gates ka computation. So if you have x here, okay. So you take the Z, like if you have like a three kind of like system, like three qubit system, you have to change the value on the middlemost one. So that's the whole representation here. So if you have X here, you take the X1, X gate first, then you take the H gate, which is the Hamrod gate, and then you perform like two more X gates here, and then finally you measure. So let's like use an actual qubit here and measure this whole system. So if you have 0, 0, 1, okay, which is shown here, and first thing what you do is you take 0 here, okay, and you first up take this X product, okay, or the X gate here. So if you take the X gate, 0 will flip and you get 1 instead. So the middlemost value will change to 1 because it's an X gate. But like once you take the H gate again, okay, there's a 1, 1 second. Um, yeah. So, there's a 1 here now. Okay. And when you take an H, 1 becomes essentially minus 1. I mean, not minus 1, but minus. So that's how you write it. Okay. And then you can simplify this. So if you have like a 0 and if you have a minus and if you have 1, you can take a tensor product of the whole ket vector system. So minus can be written, okay, like if you go back, okay, the minus axis had an equation, which is this. So you take the tensor product of the same, okay, when you deal with like the edge gate. So to simplify this, eventually you get this. So this part, okay, phi 2, after the operation of the edge gate, you get this is the value which you get. And then finally, like you apply two X gates here. So I'll just show you here. So this is for the first one and the last one. So if you apply X gates at the first and the last one, so these two values will become 1 and the last ones will become 0. So they're just like inverting themselves. So it's a NOT gate basically. So your phi 3 value will become this. Then finally what you do is you take the measurement of all the three superpositions. And then that is the answer which you get. So at phi 4, okay, um, you will be getting this is the value. So what it translates to, okay, essentially is that the superposition of 1, 0, 0 or the ket vector 1, 0, 0, it will be half, okay, and the ket vector 1, 1, 0 will be half. Why? How we getting half is that we have the magnitude as 1 over root 2. So if you take the square of it, you get half. So that's what it says here, basically. The coefficients give you the probability. So your half is your indication that your ket vector 1, 0, 0 will be half and ket vector 1, 1, 0 will be half. So that is the whole concept about quantum circuits and quantum gates. It's very step by step and it's not that easy to solve because unlike Boolean algebra, you can like just figure it out here itself. Like if you have 0, you have like a NOT gate, it will be just 1. But like we have more complex gates here and they deal with like matrix multiplication. Hence, it's not that easy to just directly write the answer, but it takes like step by step. And you need to also know the equations of the axes. Like for example, here, what we did was when you got minus here, you wrote the minus form of the equation, like the minus axis of the equation, and we took a tensor product of the same because the Hamrod gate changes the phase. So you got like a qubit, which was in two different phases. So like not two different phases, but like a different phase of the original one. So that's the whole concept about like a quantum circuit. Um, Now coming to like a different like level where you call them like multi-qubit gates. So all of the gates you've seen till now deal with a single qubit. Like even here for now, Okay, so here what you're dealing is like only like one gate, right? Like it doesn't like affect the other qubit. So or this other ket vector, I mean to say. So that is the whole single kind of like qubit gates. But now let's like come to like multi-qubit gates where you're dealing with multiple qubits at the same time. So the first gate is called a controlled NOT or the controlled X. So the NOT gate and the X gate is the same thing. So, but you prefer to use the term controlled NOT. So what it does is, let's just say if this is your target line and this is your control line. So it's like a multiplexer in Boolean algebra, wherein based on that selection, it'll choose the value. So it's like if the control, okay, is like one, okay, again, if the control qubit is one here, okay, it will basically change the value of the target qubit. So it's a controlled X gate. So it'll depend on one more qubit. So this is like a big mathematical like gate what do you call it expression and solving it like using the C naught gate. So let's just say you have like this kind of like a qubit wherein you have ket vector 0, 0, 0, 1, 1, 0, and 1, 1. So for each time you're applying the control NOT circuit. So the thing in yellow here is your control bit and control qubit, and the thing in red is your target qubit. So the control NOT will only change the value of the target one if it has the control bit value is one. So in this case here, okay, your control bit value is 0. So it won't change the target bit. Again, here the control bit value is 0. So it won't change these ones. They will remain the same. You're not making any operation. But once you have a control bit as 1, it's going to change this value. So if it is 1, 0, you get 1, 1 here. And if it is 1, 1, you get 1, 0. So that's how a whole C naught gate works or a controlled NOT gate works. This is another example of the same, wherein even if you have like multiple bits, but it only works on 2 bits. So you have to specify the target and you have to specify the control. Um, so again, like this is your whole C naught operator. Um, Now coming to like this gate, okay, it has two things. So you have two control bits here, and they both need to be kind of like one. So again, like second and the third one here are control, and the fourth one is the target. So if you have 0 and 1, okay, it won't necessarily change here. But if you have both as 1, okay, it makes a change here. Okay, so this is like the Toffoli gate. I forgot to mention this is the Toffoli gate. Okay, um this is like a more advanced form of the C naught gate. So again, like the C naught gate was dealing with this X gate or the NOT gate. So similarly, we can have controlled versions of like multiple single qubit gates. That is your Y gate, Z gate, S gate, T gate, and even the H gate. So these gates will be only functional if your control value is like 1. Okay, so this is the whole concept about your control gates for when it comes to multiple qubits. So controlled Y is written as CY. So that's like one concept. Yeah, I think that's the whole fundamentals about quantum gates, single bit and multi-bit, and its application, which is your quantum circuits. Now coming to like few good points which are there when it comes to like measurement. Okay, like the last part of the quantum circuits here. Like I think this was already mentioned, but since it's a very important point, like so when you measure like a quantum system, so it collapses into the measured state. So it no longer is like superimposed. So if we like take a photon, for example, which it has like both, like a what it's like both, like vertically and horizontally polarized. So if we choose only to like measure like either the vertical one, okay, there is no basically horizontal polarization because we've already chosen to measure the vertical polarization. So it collapses into that particular polarized state. Similarly, if we have like a qubit, and if you're measuring it like in one way, like I just say we are measuring it on the ket vector 0 axis, it'll cease there. It will not. It'll stop to become like a superimposition. So that's the whole concept about like measurement and how we can't necessarily like measure a qubit because it just collapses into its state. So uh, yeah, so when you measure it, it's only either a zero or a one. So if you were to measure it uh, so if you write it in like the alpha beta format, we would not measure it in alpha or beta, but it would be like a single form of measurement, either a zero or a one. And that time it would cease to become a qubit because it's just a Boolean variable. So that's the whole concept about like quantum gates and quantum circuits. And the whole explanation why measuring a qubit collapses its superimposition. That's it. Like that's it from my end.
Thanks for the lecture, Athar. If anyone